All right, so look, we got this car. The mass is 1,500 kilograms. Starts from rest. V initial is 0. The car accelerates, and we're told that V final is 18 meters per second. And then this happens over a time of 12 seconds. All right, so a few things we're going to need. A few things that we'll need for this problem that I'm going to solve for them with kinematics. There's really no way, I mean, I hate to say no way because a lot of times you can do things multiple ways in physics, but we're going to need to know how far it is from start to end, you know, from 0 meter per second to 18 meters per second. What's the displacement, right? So how do we get that? Use a kinematic. So for that, I would go x equals 1/2 Vf plus V initial times t. V initial is 0, so you take V final and multiply by time, and we get a displacement of 108 meters. So the displacement of the car is 108. The other thing is the acceleration. We can get acceleration from a kinematic. Vf equals V initial plus AT. V initial is 0. So A is Vf over t. So take final velocity divided by 12 seconds, and the acceleration is 1.5 meter per second squared. Okay, so now part A wants us to find the, where does it say? So assume the air resistance remains constant at 400. Find the average power of the engine from beginning to end, the average power. You know, why do they say average power? Find the average power. Well, look, where's power going to be greatest? Is the power going to be greatest over here or over here? To the right. The faster the guy's going, you know, to maintain that acceleration, you know, just think about it. If he kept going faster, 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 to maintain that acceleration is going to take more energy, right? So the farther he is to the right, the greater the power is. You know, to move an object from rest, you know, it's not as to accelerate an object from rest is not as difficult as it is to accelerate an object that's already moving. Okay. So anyway, the average power. So what's our definition of power? I would look at it this way. You know, power equals work over time. In fact, hold on. That's going to get in my way. Put it over here. Power equals work over time. Now, what's the other way to look at power? There's a second way you could look at it. Power is energy over time. Both of these would work for this problem. You know, like, is the car gaining energy? Yeah, it's gaining kinetic energy. But the thing you have to factor into this, which I'm going to solve it first this way. I like this way better. But this gets a little tricky because this problem has friction in it. There's a resistive force. So you also, the energy gained by the car is not just the kinetic energy, but it's also the loss of energy due to friction. Like, because the car is fighting against friction, right? So let's solve this with work per time. So we have power equals work over time. So we're looking for the power of the engine, right? So this is going to be work of the engine. If you're solving for power of the engine, you're going to take work done by the engine divided by time. Well, what's the work equation? Work equals what? Force times displacement. And that's going to be force of engine. So now we have everything except the force of the engine, right? Do we know how far the car went? Yeah. Do we have the time? Yep. So what we got to do is solve for the force of the engine. So let's do a free body diagram. So we have force of engine to the right, and then the problem tells us that there's a frictional force to the left, a resistive force. And it stays constant. It says constant at 400. All right, then we have mg down, which we're not going to use for this problem, and then normal force up. Okay? Is mg doing any work? No, because it's perpendicular to the motion. Does normal force do any work? No, it's perpendicular to the motion. All right, so how do we find the force of the engine? Well, to get the force of the engine, we can sum the forces in the x direction. So force of engine minus the 400 Newton resistive force is going to equal MA. Right? We sum the forces for this. So the force of the engine is going to equal MA plus 400. So you plug in M, we have our A, and we get force of engine equal to 2,650 newtons. So we bring that up here. We go, okay, force of engine is 2,650. The displacement was 108, and the time that took was 12 seconds. So this gives us a power output of 23,850 watts. Hey, and the textbook likes horsepower. I think in the back they gave these answers in horsepower. So how do you convert watts to horsepower? 1 horsepower is 746 watts. So divide that by 746, and you get 32 horsepower. Is that, did they put horsepower in the back? They did. Some of them are in watts. Okay, so that's part A. And then look, how would you do this with energy? You also could have said power is energy per time. So can I erase that? Everybody got that copied? So to do it this way, power of the engine is going to be equal to the energy supplied by the engine over time. Well, look, what type of energy is the car gaining? It's gaining kinetic, right? No potential because it didn't go up a hill. But the other thing you have to add to this is the energy that friction stole. What's the energy that friction stole? It's the work of friction, the work of that 400 Newton force, right? As this car accelerates, friction is there going like this, going sucking up all the energy, or not all the energy, but sucking up some of the energy. Okay, so if you plug into this, you'd go 1/2 mv squared, and then what's work of friction? That's going to be plus 400 newtons times the 108, right, divided by the time. So if you plug into that, you'll get the exact same answer. But I think it's, for this problem here, I think it's nicer to say work per time. Okay, part B, and then we're done. So what's the instantaneous power at this point right here? So it says the instantaneous power output of the engine at t equals 12, right over here, just before the car stops accelerating. All right, so if you look at power this way, power equals work over time. Because instantaneous means like at a specific moment. So we're not going to be able to just go, force times displacement, because this displacement is what? It's the whole thing, right? Is that going to give us instantaneous? Because we're using the displacement from the whole thing. But watch what happens here. What is displacement over time? Displacement over time is what? Velocity. So this becomes force times velocity. Dudes, do we know precisely the force of the engine at this moment right here? At that moment right there, do we know the force of the engine? Yeah, we already solved for it. It is 2,650. It doesn't change. Do we know precisely the velocity at this moment? Yeah. So if we go force times velocity, that's going to give us instantaneous power. So the force is 2,650 newtons. The velocity is 18 meter per second. So this gives an instantaneous power of 47,700 watts. So you just need to set up an equation where you can use instantaneous values. What's the force precise, like right there, what's the force of the engine? Boom, we got it. What's the velocity of the engine? Boom, we got it. So this is equivalent to 64 horsepower. Close that.